Okay, so let's think about the night sky for a second. You look up, you see all those stars, right? Galaxies, maybe some fuzz, which is a nebula.
Yeah.
It's this amazing cosmic view.
Absolutely stunning.
But then there are those absences, the spots where light just seems to vanish, black holes.
The ultimate voids, traditionally.
Exactly. And we've always pictured them as these like bottomless pits leading down to a single point, the singularity, infinite density, infinite gravity.
A mathematical point where physics kind of breaks down.
Right. But what if? What if that picture's missing something huge? What if it's not just about mass and gravity, but about something really common, like heat?
Ah, now that's a fascinating twist. Imagine if heat itself, the energy in your coffee cup,
Yeah.
imagine it actually has weight. Not much, obviously, not enough for us to notice day to day.
Right. My coffee isn't creating a black hole.
Hopefully not. But on a cosmic scale, maybe that tiny weight adds up. Maybe it becomes significant.
Okay, so if heat has weight, how does that change things for black holes? Are they not cold and empty anymore?
Well, that's the core idea, isn't it? This concept suggests they might be the exact opposite. Maybe they're like these giant cosmic pressure cookers. Unbelievably hot furnaces where the thermal energy itself is actively shaping the gravity around them.
Wow. So are black holes just holes? Or are they something, I don't know, more dynamic, more fiery?
That's the big question we're diving into today. We're exploring this idea. It's called the thermogravitational theory, or TTG.
TTG. Got it. And I should stress, this isn't standard textbook stuff, is it?
Not at all. Not yet, anyway. It's speculative. It's exploratory. It's basically asking what if about gravity, energy, and space-time.
What if extreme temperature differences, these thermal gradients you mentioned, what if they can actually bend space-time too?
Exactly. Not just mass, but a sharp change from super hot to much colder. It's a really different way of thinking about gravity's source.
Okay, that is a big idea. So where does it start? What's the foundation for TTG?
Well, you always have to start with Einstein, right?
Mhm.
General relativity. It's the bedrock. GR tells us massive things warp space-time, and that warping is gravity. Planets orbit the sun because they're following the curves in space-time the sun creates.
Oh, beautiful theory. So TETG doesn't throw GR out.
No, not at all. It aims to add another layer to it. Which brings us to the first big idea in TETG.
Which is,
Thermal energy has weight.
okay, based on E's phi partial, energy equals mass times the speed of light squared.
Precisely. Energy and mass are equivalent. So any energy should have a gravitational pull. TETG really zooms in on thermal energy, the vibration of particles.
But you said the heat in my coffee cup, it's negligible.
Totally negligible in everyday life. But TETG proposes that in the most extreme places. Think collapsing stars, black holes.
Yeah.
This effect could become huge, maybe even dominant.
Dominant. Wow. Okay, so heat has weight. What's the other pillar? You mentioned gradients.
Right. This is maybe even more crucial. It's not just that there's heat, it's how it's spread out. The theory says that a really sharp thermal gradient, a steep drop in temperature over a short distance, can exert its own powerful influence on space-time. It can cause curvature.
Can you give me an analogy for that?
Sure.
Oh.
Think of a calm pond, uniformly warm, flat surface, right?
Yeah.
But now imagine you could somehow make one spot boiling hot and the spot right next to it freezing cold. You'd expect some serious turbulence, maybe waves, ripples.
Okay, I can see that.
TETG suggests something similar happens with space-time. A sharp thermal boundary creates, well, gravitational ripples, a bending. It means gravity isn't just about where mass is, but also about where energy is concentrated and how it flows. Thermodynamics becomes an active player in cosmology.
So heat distribution shapes gravity. That really changes how we think about cosmic structure formation, especially something like a black hole's birth. How does
Yeah.
that look under TETG?
Well, the beginning is familiar. A giant star runs out of fuel.
Yep.
Nuclear fusion stops pushing outwards, gravity wins, and the core starts to collapse. Standard stuff.
But then comes the TETG twist as it collapses.
It gets incredibly dense and incredibly hot.
Yeah.
Just crushing all that matter generates immense heat.
Right.
Now, according to TETG, that heat itself has gravity. So you've got the gravity from the star's mass plus the gravity from its temperature.
Ah, so the heat adds to the pull,
Exactly, which squeezes the core even harder.
which generates even more heat.
You got it. It's a positive feedback loop, a runaway process.
Thermogravitational collapse, you called it.
That's the term, yeah. Heat and gravity feeding each other. The collapse accelerates way faster than mass alone would cause. It's like the star is being crushed by the weight of its own heat.
A runaway train, you said? Physics where the brakes become accelerators.
That's a good way to think about it. So the black hole isn't born from a cold, quiet collapse. It's born in this this thermogravitational firestorm. An event horizon forms when that combined thermal and mass gravity becomes overwhelming.
Okay, so it's born hot. What about crossing that event horizon? What's inside a TETG black hole? Forget the empty void idea.
Completely forget it. The event horizon here is more like a frontier of pure energy density. Yeah. The heat is so intense, its gravity creates the trap. Think of it like a star so powerful, its escape velocity is faster than light, but it's the heat doing a lot of the work. A wall of gravity forged by heat.
And inside that wall, still not empty.
Definitely not. It's a reservoir packed with all thermal energy converted from everything that ever fell in, stars, gas, light. It all gets turned into heat, feeding the furnace.
And this creates that gradient you talked about.
A massive gradient, insanely hot, just inside the horizon, probably getting even hotter towards the center. And that gradient is the structure. It defines the interior landscape, sculpted by temperature differences.
And this intense heat and gradient, they warp space-time inside dramatically.
Absolutely. Space gets so twisted that essentially all directions point inwards. You can't go sideways, you can't go out. The geometry itself forces you deeper.
And time. What about time dilation?
Oh, it gets extreme. Just like near any massive object, time slows down relative to the outside. But here, amplified by the thermogravity, it would slow drastically.
So billions of years could pass outside while only moments tick by inside.
Potentially, yes. Deeper in, closer to the core, time might almost seem to freeze from an outside perspective. It becomes this pocket universe where time is stretched nearly to infinity by the heat.
Okay, let's talk about the very center, the singularity, that infinitely small point. It bugs physicists, right? It's where the math breaks.
It really does. It's more of a statement that our theory, general relativity, is incomplete at that point. It's not really a physical description.
So does TETG offer something cleaner, an alternative?
It offers a very compelling one, I think. Instead of an infinitely small point, TETG proposes a dense thermal core.
Okay, not a point, but a core. What's it like?
Imagine a sphere. Not infinitely small, but maybe as small as physics allows. It's made of pure, concentrated thermal energy, squeezed to the absolute maximum possible density and temperature by its own thermogravity. Think of it as the ultimate boiling energy state.
But wouldn't even that want to collapse further? How does it stay stable? How does it avoid becoming a singularity?
Well, think about what extreme heat does. It creates pressure, right? Like in the core of a star, heat pushes outwards.
Okay.
TETG suggests this ultra-dense thermal core generates an immense outward pressure from its own energy. This pressure could potentially balance the crushing inward pull of thermogravity.
Ah, like a standoff.
Equilibrium.
Exactly, a stable balance. The core finds a size, likely incredibly small but finite, where the inward gravity and outward thermal pressure are perfectly matched. It wouldn't violate physics, it would be governed by it.
So you swap a mathematical breakdown, the singularity, for an extreme but physical object,
Yes.
a balanced core of pure energy. That's the idea. It makes the black hole seem less like a cosmic error and more like a stable, final configuration of energy and gravity. The heart of darkness might actually be, in a way, brilliantly energetic.
That is a radically different picture. Okay, so what happens to stuff falling in? You mentioned spaghettification.
Right, that still happens first. Tidal forces stretch things into strands. In TETG, with the added thermal gravity, maybe even more violently, but that's just the start.
What's the ultimate fate? Just getting crushed?
No, it's more fundamental.
Sure.
As that shredded matter plunges deeper into the superheated interior, the temperatures and pressures become unimaginable. Atoms get ripped apart, nuclei break down.
Okay.
But then, the key step in TETG, the distinction between matter and energy completely blurs. Einstein kicks in completely. The mass of the infalling stuff is converted, totally and efficiently, into more thermal energy.
So a star doesn't stay a star, or even subatomic particles. It just becomes heat added to the reservoir.
Exactly. It feeds the furnace. Its entire mass energy joins the thermal bath inside. And light, photons falling in. Same deal. Their energy gets absorbed, trapped by the curved spacetime, adding to the total heat content.
And this trapped energy reinforces the black hole's gravity.
It has to. More energy means more thermogravitational effect, strengthening the event horizon, making the prison even more secure. Nothing retains its original form. It's total assimilation.
The ultimate recycling system and the ultimate prison. Wow, okay, this is an amazing theoretical picture. But how on earth could we test it? How do we look for evidence?
Yeah, that's the million-dollar question for any new theory, isn't it? We need predictions, things we can actually look for.
Right.
TETG is still mostly qualitative, but it does suggest some differences from standard GR that we might be able to spot. subtle footprints in extreme environments.
Like around accretion disks? Those super hot swirls of gas falling into black holes?
Exactly. Those disks are incredibly hot. Millions, maybe billions of degrees. TETG says that intense heat should add its own bit to the local gravity, right near the event horizon.
So it would warp spacetime slightly differently than just mass would.
That's a prediction. It might cause the gas orbiting closest to the black hole to wobble in a specific way, or change the pattern of radiation coming off it compared to what standard GR predicts.
Could something like the Event Horizon Telescope see that?
Potentially. It's pushing the limits of observation, but that's the kind of precision we'd need. Look for those tiny deviations near the edge.
What else? Any other cosmic laboratories?
Pulsars are another possibility. They're incredibly precise cosmic clocks.
Right, spinning neutron stars, sending out beams.
Yeah. If we found one orbiting a black hole nice and close, we could time its pulses extremely accurately. Now, TETG predicts that the intense thermal gradient near the black hole would add an extra bit of time dilation.
Slowing the pulsar's clock down even more than GR alone predicts.
Exactly, just a tiny bit more. Detecting that anomalous slowing would be huge. It would be strong evidence that heat gradients are warping time, as TETG suggests.
That sounds incredibly difficult to find, a pulsar orbiting a black hole just right.
Oh, absolutely. It's a needle in a cosmic haystack.
And what about, dare I ask, experiments here on Earth or nearby?
Well, that's really pushing it. Probably far future stuff. But you could imagine, maybe, creating an insane concentration of energy with powerful lasers. Could we measure a minuscule gravitational field produced just by that energy? Or maybe build ultra-sensitive atomic clocks and put them in places with extreme temperature differences, see if their ticking rate changes beyond known effects. Very, very hard. But conceptually, that's how you test the core principles.
Okay, so we've got these potential tests, but it's important to circle back to where TETG stands now. You said it's speculative.
Absolutely. Crucial point. As of right now, August 18th, 2025, this is an exploratory idea. It's not in the mainstream, not accepted science.
So what's its value then, currently?
Its value is in challenging assumptions and offering potential solutions to problems, like the singularity. It makes us think differently. But it's got a long way to go.
It needs the math, right? The rigorous equations.
Desperately. Right now, it's mostly concepts, qualitative descriptions. To be a real scientific theory, it needs that solid mathematical framework. Precise equations that make quantitative predictions you can actually test against data. Without that backbone, it's still more philosophy than physics.
And we should remember, these thermogravity effects, they're tiny in normal life.
Vanishingly small.
Yeah.
Like we said, your coffee, a volcano. Doesn't matter gravitationally in any way we'd ever notice. You don't weigh more with a fever.
Thank goodness.
TETG is really a theory for the absolute extremes. Inside stars, maybe, but primarily inside black holes. That's where the temperatures and densities get high enough for these effects to potentially become dominant.
So it's not trying to replace Einstein.
Not at all. It stands on Einstein's shoulders. It's trying to add a chapter, suggesting that maybe gravity has this thermal component that becomes important only under the most intense conditions. It needs proof, rigorous math, years of scrutiny. It's a long shot, but an interesting one.
So we've journeyed from seeing black holes as cold voids to imagining them as these, well, ardent furnaces with boiling thermal cores.
Quite a shift in perspective, isn't it?
Yeah.
Replacing the singularity with this dynamic, energetic core, all driven by heat shaping gravity.
It really underscores that science isn't finished. It's always evolving. The universe's story is still being written.
Exactly. And the value of ideas like TETG, whether they turn out right or wrong, is in the questions they make us ask.
Like, is the link between energy and gravity deeper than we thought? Are thermodynamics and relativity connected in ways we haven't grasped?
Those kinds of questions are what push science forward. They remind us how much mystery is still out there.
And you, listening right now, you can be part of exploring that mystery. We live in an amazing time for access to cosmic information.
Totally. Online simulations, incredible documentaries, articles from scientists on the cutting edge. You can really dive in.
You don't have to just be a spectator. You can explore these ideas yourself. So keep asking, what if?
Yeah, next time you look at the night sky, don't just see the stars. Imagine those invisible forces, mass, yes, but maybe also heat and energy gradients, weaving everything together.
This deep dive into thermogravity is just one possible storyline. The universe's true nature, that's still being uncovered. The biggest discoveries are definitely yet to come.
The cosmos awaits.